Hi folks, today we're going to be working on some intermediate problems involving logarithms. So we're going to get started with some warm-up problems just to make sure we have that definition of logarithms down and how it works back and forth between that and exponential functions. So let's get started. Write the log base x of b equals y in exponential form. So from the definition of logarithms, we know that x value down in the base, the logarithm, that'll become our exponent. So what that means is that we should have x raised to some power. And where does the exponent come from? Well, it comes from the other side of the equal sign. So it's going to be that y value. So we have x representing base, and then y is our exponent. So that means we have our exponential equation being x to the y equals b. All right, so let's move on to another problem. Write 7 to the 100th power equals x in logarithmic form. So notice if we have a base for an exponent, that should be our base for our logarithm. So we have that 7 should be our base for our logarithm. And then on top of that, we have that 100 being the exponent. So that should be on the other side of the equal sign when we have our logarithm involved. So that means we end up finishing with log base 7 of x equals 100. That is 7 to the 100th equals x in logarithmic form. All right, taking a look at our third problem. Evaluate 17 to the log base 17 of 423. So this might freak us out at first. We have log base 17 of 423. We don't know what 17 to what power gives us 423, but actually if we have our properties of logarithms in place, we don't even have to worry about that. So from our properties of logarithms, notice if the base of your exponential function there and the base of your logarithm are the same, they essentially just cancel out and leave you with the term that's up in parentheses there. So at the end of the day, notice we have 17 matching in both places, so our answer is just 423 by properties of logarithms. So it kind of shows you why we want to learn those properties of logarithms. Makes our lives a lot easier in terms of these problems. Okay, moving forward. Determine the domain of the function f of x equals log base 5 of x squared minus 9 plus 13. Okay, when it comes to domain, where do we have to worry about things? Well, the plus 13 will not play a role whatsoever in terms of the domain, and that 5 in that base of the logarithm really doesn't play a role either. What plays the role is the inside of the parentheses, that x squared minus 9. In order for this to be defined, this function here, we need x squared minus 9 to be greater than 0. That's just how logarithms are defined. We need that inside a logarithm to be greater than 0. Because remember, it is some value that's been raised to an exponent, some base raised to an exponent. And remember, our exponential functions are always positive, essentially. So now, moving forward from here, it might help if we just rewrite this. X squared minus 9 can be factored to x plus 3 and x minus 3. And when you think about that, we talk about critical values oftentimes. So the critical points in this case, we just set it equal to 0, and you get x equals negative 3 and positive 3. So if you were to have created an interval, what have we done? Well, the negative 3 and positive 3 allow us to break the interval into or break the real numbers into 3 different intervals. In those 3 intervals, if we exclude negative 3 and 3 from those, we end up getting our test intervals, is what we often call them. And so our test intervals are negative infinity to negative 3. And then our second test interval is negative 3 to positive 3. And our third test interval is 3 to positive infinity. So with these test intervals, all we do is we pick a value in there and plug it into our x squared minus 9, or which is equivalent to x plus 3, that quantity, and then x minus 3. And so we just figure out if it's positive or negative, and that'll tell us everything in terms of whether or not these are satisfied. So we'll begin by testing the interval negative infinity to negative 3. So if you plug that in to x squared minus 9, or as we mentioned before, the quantity x plus 3 times the quantity x minus 3, you end up getting a positive number. And for example, if you plug in, say, -4, -4 the quantity squared is 16, minus 9 is 7, and 7 is a positive number. So actually, and notice 7 is greater than 0. So everything in that interval, -infinity to -3, there was nothing special about me choosing -4 there. Everything within that interval is going to satisfy this inequality. So that's a good one. We'll kind of mark that as one of our ones to use. Okay. So now with our next one, -3 and +3, we can test another number with that. So pick a number inside that interval. We'll pick 0. If you plug that into our equation, 0 squared minus 9, notice you get -9. That is a negative number, so it's not greater than 0, so it's not going to satisfy our inequality. So for the -3 to 3, we've got a problem. That one's not working for us. So the last interval we're going to work with is the 3 to infinity. Just pick some number inside that interval. It doesn't matter what it is. We'll pick 10, for example, this time. If you plug in 10, you get 10 squared is 100 minus 9 when we're plugging it into that original x squared minus 9 equation. So 100 minus 9 is 91. That's a positive number. That's all we care about, is that it's positive, because larger than 0 means positive. So since it's positive, it's going to satisfy this inequality. And that means everything from 3 to infinity will actually satisfy that inequality. So we have two intervals. You have that interval -infinity to -3, and you have the interval 3 to infinity, both of which satisfy our inequality. What does that mean at the end of the day? Well, it means that our domain is given by this interval -infinity to -3 union 3 to infinity. Okay, so hopefully that makes sense on that problem. Let's move forward to our next type of problem. So let's evaluate the log base 1/64 of 1/4. And there's a few different ways to do this. Notice we already have fractions in both cases. So what happens here, just with the fractions being between 0 and 1, that also means, the way this looks, we should finish with a number between 0 and 1. And some people struggle with that concept, so we're going to take a slightly different approach here, and we're going to try and use exponential forms. So first off, if we're going to try and use exponential forms, one way to do that is let it be equal to y. So if y equals log base 1/64 of 1/4, then the exponential form is that 1/64 to the yth power equals 1/4. And if we want to work with this, probably an easier way, fractions tend to freak out people. So notice 64 is 4 cubed, right? And so we could write this instead of 1/4 cubed as 4 to the -3. And then 1/4 can just be 4 to the -1. So you get 4 to the -3, that raised to the yth power, and then 4 to the -1. So now we have our nice little equations. And notice with our exponential properties on that left-hand side, we can write that as 4 to the -3y equals 4 to the -1. And this allows us to use our one-to-one property. And so our one-to-one property basically says you can drop the bases of the exponents, and all we need to do is say -3y equals -1. And solving for that, just divide both sides by -3, and you get -1 over -3, which the negatives cancel, and you get y equals 1/3 as a solution. And just as we suggested, it's a number between 0 and 1. So just keep it in mind, and there's different ways to have done this. By the way, you might have wanted to use 2 to some power. That would work as well. You'd get essentially 2 to the -6y equals 2 to the -2. And notice that still reduces down to y equals 1/3. So it didn't matter as long as you found some common base to work with. We were good from there, essentially. So yeah, if you have any other ideas on this, feel free to test them out and see what happens. It just depends how good you are at playing with these different exponents. All right, moving forward. Recall that a googol is 10 to the 100th power, and we want to determine the log of googol. So remember, a logarithm is just a log base 10, so we can rewrite this as the log base 10 of the log base 10 of 10 to the 100. Just making the appropriate substitutions, And now we can use our properties of logarithms essentially. Since our base of our logarithm matches the exponent space, those things essentially cancel. So this basically becomes just log base 10 of 100. Okay, so now another way to write log base 10 of 100 is log base 10 of 10 squared. And we can reuse that same property, the 10s in the base of the logarithm, and the 10 for the base for our exponential is the same, so we get our final answer of this just equaling 2. And the reason I like this problem personally is when you look at it, it's something you can't punch into a calculator and get an answer necessarily. So some of the calculators, they aren't capable of making this calculation because 10 to the 100th is too big. But we can do this in our head, and it only takes just a few minutes, if that, just by knowing our properties of logarithms. Okay, last but not least, our last problem here, we want to determine a logarithmic function of the form f of x equals log base b of the quantity x plus c plus some k on the outside, where b, c, and k are constants that represents the graph appearing below. So there's some different routes here. But what we'll do is we'll kind of get the ball rolling here by just thinking about what's going on. So we have this B, C, and K. But if you notice, the first thing I'd pay attention to in the graph is that you have a vertical asymptote at x equals -2. So what does that mean? Well, usually a logarithm, if there was no shifting going on, just a regular logarithm has a vertical asymptote, my apologies, vertical asymptote at x equals 0. And in this case, we've shifted that left 2 units. So what that means, if we shifted it left 2 units, we have c equals 2, because x plus 2 on the inside is a shift left, if you recall, from your transformations of graphs information. All right, so now that we have that in play, we can start using some points. And so let's look at some nice points on the graph. Well, notice the point -1, -1 appears right on the graph. And so we're going to use that. And if we have that, we can plug it into our equation. So we know -1 is the y value, so we get -1 equals log base b of the x value is also -1 there, so we get -1 plus 2 plus some k. Now we might look pretty troublesome because we have a log base b of 1 essentially plus k, but if you remember from the properties of logarithms, the log base b of 1 equals 0. So that means -1 equals k. So we've solved for another variable along the way. So we've got 2 variables down, 1 to go. And what we'll basically need is just one more point to do it. And there's a couple ways to go about this. And we didn't have to use -1, -1, by the way. We could have used something like 2, 1, and then also 0, 0. So it doesn't matter here how we go about it. But so let's take a look at 0, 0 for our next point. So if we use 0, 0, what do we need to do is basically just the same thing we did before, plug them in for our x and y values. So we get 0 equals log base b of 0 plus 2, and then we plugged in that k equaling -1 there. So what this means is 0 equals log base b of 2. Well, the exponential form of that means we get b to the 1 equals 2. And if b equals 2, well, notice we have our function. We have the b, we have the c, we have the k. So we have all our values. And so this means f of x equals log base 2 of the quantity x plus 2 minus 1. And that's our final answer.